Hey guys, Mr. Bowman here. We're looking at 2.12 probability methods in this video, and we're focusing on all the excellence questions from that 2017 exam. We're going to get straight into question number 6, and regular surveys taken from New Zealanders to find out the state of their health and well-being. A sample of 2,500 young adults between 15 and 24 resulted in all of this result. So it's a two-way table. Look at the variables, so it's whether or not they are obese or not, and if they are male or female. A newspaper article has the below, and then it says about the survey that a recent study of young adults aged between 15 and 24 shows that females are 20% more likely to be obese than their male counterparts. So just reading through this, so it says more than 20%. So we're looking for a number greater than 20%. Do you agree with this article's introduction? So it is a relative risk question, and we've got that keyword. They've very specifically added in more than 20%. So let's go ahead, see if we can get to that number. So first thing, we're comparing whether or not someone is obese based on their gender. So the first thing we need to find out is what is the probability that someone is obese given that they are female. And we then need to do the same. We need to find the probability that someone is obese given that they were male. So in the first one, we only care about the females, and down below we only care about the males, and that should allow us to make that comparison. So for these questions, we always do our F over T type approach, and the T relates to the number of females, and this time around we've got 1,295 females. 1,295. Of those, 285 are obese. So that's 285. Put that into your calculator, and you're going to get 0.2201, and that was with a 4DP rounding. We now need to do the same with the males. So we're going to do our F over T approach. We know that there's 1,005 males, so that's our denominator. So 1,205 males. Of that, how many are obese? 222 over there. 222. Find the probability from that, and we're getting 0.1842. And again, I've rounded that to 4 decimal points. Once you've got your two conditional probabilities, you then jump into your relative risk. So let's go ahead and find that. So relative risk, just a reminder, I always encourage us to do big over small. And in our case, we're going 0.2201 divided by 0.1842, and that gets us to 1.1949. So what that means is females are 1.1949 times more likely to be obese than their male counterparts. So let's explain that. So this means that females from the study, so probably should reference, it's not all females, just females from the study or from the survey. From the survey, 1.1949 times more likely to be obese than their male counterparts. So if you stop at that point, that gets you the merit when you interpret that relative risk. Our question doesn't ask about relative risk. It states, or it's asking you about whether or not you agree with the article's introduction. And the key part of this is the 1949 part of it. So there would be 0.1949. If you times that by 100 to get to a percentage, you're going to get 19.49%. So we now need to look, is that more than 20%? In this case, definitely not. It is very close to 20%, but less than 20%. If this article said females are approximately 20% more likely to be obese than their male counterparts, I'd probably agree with it because that number's pretty close. They are very specific about it needing to be more than 20%. And then from that, we can say, as a result, females are 19.49% more likely to be obese. I mean, the kicker, linking it back to the article, which is not more than 20% stated in the article. And then just finishing, just to wrap up, just going to do it over here. I therefore disagree with the article's introduction. I therefore disagree with the article's introduction. So a wordy question, so definitely more wordy questions in the excellent stuffs, but hopefully this one makes sense. We are now looking at question number 7, and we've got merino ewes produce lambs, so similar kind of merino sheep type question that we've seen in the other ones. A long-term study shows that 65% of merino ewes produce a single lamb. Of those lambs, 86 survive until they are weaned. Of the ewes that produce twins, about 1 in 5 of those lambs, 1 in 5 lose both before they're weaned. That means they both pass away, and an equal number of one twin or both twins survives until they are weaned. What is the probability that a randomly selected lamb survives until it is weaned will be from a single lamb? This question is going to be a bit messy. Even though we're interested in the lambs, we're actually going to do a probability tree based around the ewes. So first thing is, the birth can be single or it can be twins. And we've been told that 65% of them will be single births, so that's 0.65, which means the remaining 0.35 will be twins. Once we've got that, this one here, they either, we'll call it survive or S- not survive. And we've been told 86% will survive if they are from a single one. So that's 0.86, which means S- not surviving 0.14. Now that we've done that, the twins is a bit more tricky because you could have one lamb surviving. So 1 survive, 2 survive, or S-, they both don't survive. So we're now going to go back to the questions. 1 in 20 lose both lambs. So 1 in 5, so that's 0.2. And it said it's an equal number between one surviving and both surviving. So their remainder 0.8 will be split up into 0.4 and 0.4. And the question specifically has asked us what probability of randomly selected lambs will survive until it's weaned that was produced from a single lamb. So exploring that, all of the lambs that survived would have come from these 3 branches. So we need to find the probability of those 3 branches. This one here would be 0.65 times 0.86, which is equal to 0.559. This one down here is 0.35 times 0.4. Just a reminder, that comes from the branches leading up to it, which is 0.14. And this time around, 2 surviving. Just over here, I just want to write, because there's 2 surviving, we're going to double this number because there are 2 lots of lambs coming from this particular pathway. So we're going to go 0.35 times 0.4. Notice that would be the same as the single lambs, but we're going to multiply that by 2 because there's 2 lambs, which gets us to 0.28. So that was the trick that came from this one. Because that branch represented multiple sheep or multiple lambs surviving, we needed to double that in terms of our probabilities. We've now been asked, so of the lambs that survive, so these are all of the lambs that survive. We're dealing with, decimals and points, but the ratios will be the same if they were whole numbers. So probability that they are from a single birth if they survived. And think about F over T, that's what makes this question really tricky. The denominator, or the total outcomes, will be the addition of all of the numbers that we calculated above, because that would be the proportion of lambs. So that's 0.559 plus 0.14 plus 0.28. And of all of these, how many were from a single birth? And that would just be the number on the top, which is 0.559. Plug that into your calculator. If you are doing that, make sure you wrap brackets around the denominator, or else you might get a wrong answer. That comes up to 0.5710, and that had a 4 dp rounding. So what that means is about 50% of the lambs that are born come from single births. The remainder would come from those two twin scenarios, which are less likely to occur in the first place. We are now looking at question number 8, which does follow on from question number 7, so I have left that probability that we would have drawn beforehand. So the lambing percentage is the number of lambs that survive until they are weaned compared with the number of breeding ewes. So it's the number of lambs divided by the breeding ewes. This is often expressed as a percentage, and in our case it is known that 85% of breeding merinos actually produce lambs. What is the lambing percentage for this particular study? So our lambing percentage would be a proportion of the overall herd. So if there was, say, 100% of the merinos, that as a probability would be 1. And that is divided by the number of lambs that come from all these scenarios. So adding up all of those would be the proportionate number of lambs that results. So we're going to have 559 plus 0.14 plus 0.28. This time around, we know that only 85% of these are actually breeding. So this 1, which represents every single lamb, or 100%, we know that's not right. What we're going to do is we're going to times that by 0.85, because we know a portion of them won't be breeding. We put that into the calculator, we're going to get 0.83215. Just a reminder, we've been asked about a percentage, so what I'll be doing is I'll be timesing that by 100, so that would get me to 83.215%. We are now up to question number 9, and salmon are grown in sea pens. Each pen contains several thousand salmon. After 1 year in the pens, male salmon have weights that are approximately normally distributed, with a mean of that and a standard deviation of that. After 1 year in the pens, so this is 1 year later, which suggests these numbers here are all going to change because fish will come and go, and they'll grow and maybe give birth to smaller baby fish as well. So we've got salmon, female salmon. So we're now talking about, that was talking about male. We're now talking about female. They've got a mean weight of this number here. If 40% of the salmon exceed 4,000 grams, what would the standard deviation be? So this question, we are looking to find the standard deviation. And as always, we draw our curve. We know the mean is 3975. We don't know the standard deviation here, so we'll pop that as a question mark. And we know that 40% exceed, so exceed means larger, 0.4, than that 4,000 gram limit that they put on. When you're doing these types of inverse questions for the mean or the standard deviation, either of those circled ones, you do need to convert it to a standard normal curve to find a z value. So in a standard curve, we know that the standard deviation is 1, and we know that the mean is 0. We don't know the z value, but we know that there is still 0.4. So when we think about our calculator, This is an inverse normal question now. The tail is going to be a right tail. The area is that 0.4, that shaded part. The standard deviation is 1 and the mean is equal to 0. If we pop that into our calculator, we're getting a Z value of 0.2533. And when you get to your Z value, it's really important to check it makes sense, because this number here is 0, which means anything here has to be positive, which is the case for us, and anything in the other direction has to be negative. If we had a negative number here, we should know that we've done something a bit wrong. Once you've got to that step there, we now need to rely on our Z formula. So Z is equal to X minus the mean divided by the standard deviation. 0.2533 is going to be equal to X, which comes from the 4,000 in the original one, the mean, which comes from the original graph, and the standard deviation is the variable we don't know. So that's going to be 4,000 minus 3975 divided by the standard deviation. If you're using the graphics calculator, make sure you wrap that top in brackets to get the right answer. And your answer should be 98.7 grams. And that there had a 1 dp rounding. I think this question, it comes up every single exam. It's one that we should all be aiming for. Could be the mean, could be the standard deviation, but a really, really good excellence question to aim for. And now looking at question number 10. And question number 10, another really typical excellence question that comes up. And this time around, we're dealing with a salmon again. And they're expected to have a normal distribution curve that looks a bit like this. We've taken a random sample, and that sample showed us that the weights looked a bit like this. Compare the probability and the histogram that resulted in the shape. So it's trying to say compare this and this. And when you're doing that, you're basically trying to say, well, is this normally distributed or is it something else? When we're doing this type of question, I do encourage us to think about our inferences where you've got to talk about the center, you've got to talk about the shape, you've got to talk about the spread and anything interesting. We needed to do that. This time around, because we're dealing with probability distributions, we should also do a probability comparison as well. So let's get into it. Let's have a look at the center. And in a normal distribution model, our center, you can kind of see up and down, it should be in the middle of our graph. And that is suggestive of some element of symmetry. So if the center is in the middle, there's going to be fairly symmetrical on either side of it. So figure 1 is symmetrical, whereas our sample in figure 2 is not symmetrical. Oh gosh, not having a good day spelling. They're about symmetrical. So what that tells us, in figure 1, the mean and the median are probably going to be the same. In figure 1, the mean and median will be similar or the same. However, the skew in figure 2 will mean the mean and median may not be similar. Yeah, so just a reminder, if there's a bit of a skew, so we can see there's a bit of a tail here, that normally alters the mean relative to the median. So we've had a look at center. We're now going to look at the shape, and we've already done a bit of that in the center discussion. And then we could just say, as above, our sample is not symmetrical. In addition to that, we might want to be specific. It does look like there's going to be a right tail. So figure 2 appears to have a right tail. A right tail with two peaks. Should be contrasted with kind of even tails and kind of one peak over here. So we've done the shape. We're now going to have a look at the spread. And when we're talking about the spread, I'm probably going to refer to the range, just because we don't really have any information on the interquartile range. But we can see this goes from 3,800 up to about 4,300. So that gives us a range of 500. Down here, we're 3,850 going all the way up to 4,200. And that gives us a range of about 350. So there's quite a big difference between these, and you would expect the ranges to be fairly similar. So the range for figure 1 is 500 grams, because that's our units, which is significantly larger than the range in figure 2 of 350 grams. So yeah, key difference. We definitely expect a similar type of range. To then have a look at anything else interesting, and just to help with this discussion, I'm actually going to flip back a slide, which I don't do a lot in these videos. But we can see the males had a mean of 4,125, and the females had a mean of 3,075. So let's go back. So males, just to confirm, had 4,125, and females was 3,975. So quite a big difference here, and that might explain the group that we had. So we can kind of see two groups of data. So because the females are smaller, they could be that group there, and the males could be that bigger group there, and that doesn't really come about in figure 1. We know that male salmon tend to be larger than female salmon, which is shown in figure 2, where there appears to be two groups. Where there appears to be two groups. So that kind of runs through that interesting feature. So that's the discussion or the comparison part of it that we need. So based on that, it's probably not going to be a normal distribution because the ranges are all different. There appears to be groups. There's just a lot of differences to that normal distribution. The next step you need to do, and this is the one which deviates from the inferences internal, is you need to calculate a probability. So what we're going to do is we're going to estimate a probability from both graphs, and we're just going to make a comparison to see if they are similar. If they're similar, that probably suggests, well, maybe we do have a normal distribution on our hands. If they're really different, that probably tells you, well, you don't have a normal distribution on your hands. Cleared our first discussion to carry on. So we're now going to look at probability, and so in figure 1, it appears that 50% of salmon weigh more than 4,050 grams. And I've used my understanding of normal distribution curves to get that number. So down the middle, which is about 4,050, I know a normal distribution curve, 50% should be this way, 50% should be this way. So I'm looking at more than 50%. I'm now going to calculate, well, how many salmon weigh more than 50% in this sample. So we can see we've got 14 over here, we've got 10 over here, and we've got 4 over here. So if you add those together, that gets you to 28, and that's out of a sample of 50, which is going to be 56%. So that's our next thing. So in figure 2, 56% of salmon weigh more than 4,050 grams. And we could probably go on to say this is fairly similar but slightly skewed by the male grouping. Okay, so that wraps up our comparison. So we don't necessarily need to state if this is normally distributed compared to this. What we've done is we've done a bit of a comparison comparing figure 1 and figure 2, and we've made some observations and used a bit of context and numbers from the graph on the way. So hopefully you found these videos or these questions useful. That was all the excellence questions from the 2017 exam. Thanks so much for watching, guys. Now let's keep practicing.